Good morning, chemistry team. Your chemistry coach is coming at you. Video number 7 in our electrochemistry series. All right, so we have been looking at how to draw cell diagrams and electrochemical cells and line notation and all that fun stuff, and looking at the potential difference between reduction and an oxidation half cell, right? We always put the anodes on the left and the cathodes on the right, whether we're drawing the whole diagrams with the beakers or we're doing line notation, doesn't matter. We always do the anode on the left, cathode on the right. What we're interested in, though, is what would be the potential of one of those half cells, just the electrode itself. Oh, we got a problem here. We ran into this problem in thermodynamics a lot, too. So we're looking at individual electrode potentials. Now, we can easily go into the lab, take a voltmeter like I showed you, and measure the overall cell potential, right? That voltage between two half cells, right? It's the driving force between them. And those are pretty precise measurements. I got that to 3 decimal places, and that wasn't the greatest voltmeter ever. So those are pretty precise measurements. We can measure the overall cell potential. And we can do that at non-standard conditions. We could do that at standard conditions, although that's pretty restrictive at standard conditions, right? You have to have any solutions with an activity of 1. Molarity of 1 is probably a good representation of that. Anything that's a gas would have a pressure of 1 bar. 1 atmosphere is a pretty good representation of that. But if I want to get an individual electrode, we can't measure that directly. Oh no, right? You cannot measure an individual electrode potential for any half cell. You can't do just the anode by itself, not connected to something. You can't do the cathode by itself, not connected to something, because the whole point is the potential difference between them. If you don't have something connected to it, it doesn't mean a whole lot. You know what I mean? It's like it's a relative thing, right? So if these electrons, what's the force of the electrons to drive from the anode to cathode? But if you don't know what you're driving it to, how do you have the faintest idea what it is, right? We need a frame of reference. We run into this problem in thermodynamics too, right? We cannot measure the internal energy of a state, either here or here, but we can measure the difference between them. We can't measure the enthalpy of a system here or here in state 1 or state 2, but we can measure the difference between them. Oh, right? Same with entropy, right? Although entropy is different, we can determine entropy differences, but see, entropy is different. We can actually determine the absolute entropy at a state because of the third law of thermodynamics. That gives us a defined reference state of 0. Remember, a perfect crystal at 0 Kelvin has an entropy, right? A specific entropy of 0. You look at Boltzmann's equations. So that's different. We can define an absolute reference state of 0 for entropy, but not enthalpy or internal energy. If we had a defined reference state that had a value of 0, right? So if I could take an electrode and just say, this is 0, we would have to agree on which electrode that is, right? As a science community. If we didn't, if you said, let's use the lead electrode, and I say, well, let's use copper, and someone else says let's use hydrogen, and we all use different reference states of 0, now we got serious communication issues, and it's just total chaos. So we need a universally defined reference state. Hopefully you guys can agree with that. So the science community has treated the hydrogen as a defined reference state. So I'm going to do that on the next board. So to get an individual electrode potential for just a half cell by itself, we need that defined reference value of 0. Hopefully you can agree with that. And we're going to be doing this at standard conditions, right? So we're going to define this value of 0 at standard conditions. So any gas involved, pressure of 1 bar or 1 atmosphere, any solution, activity of 1, molarity of 1, we're going to be okay with that. Pretty limited, but in the laboratory, but very useful for calculations and theoretical stuff. So let me throw up. I'm not going to throw up. Bad choice of words. Let me write up on the next board what our reference point is of 0 that has been universally agreed upon. Be right back. All right, we got a crazy board here, but this is our defined reference state of 0, our defined reference electrode of 0. We're going to be at standard conditions here. And we have chosen as a science community hydrogen for this, all right? And we could look at it for the oxidation or the reduction because it's going to be defined as 0, so it doesn't matter if you reverse it back and forth. We'll find out if you take an electrochemical half reaction and reverse it, you just change the sign. It's the same numerical value for the E for the half cell, but you just put a negative sign in front of it. It's just electrons flowing that way or electrons flowing that way. One way spontaneous, one way is not spontaneous. Same numerical value, just change the negative sign. Similar to thermodynamic ones. You switch the equation, same number, just switch the sign. All right, so here's our definition. We have the official one and then the one everybody uses. So let's take some hydrogen gas. Since we're at standard conditions, we're going to make that a pressure of 1 bar, which is approximately 1 atmosphere, give or take. I have that in some water forming hydronium ions, right? So we're taking hydrogen in an oxidation number of 0 to an oxidation number of 1. So as written, this is an oxidation half reaction. I can flip it, make it a reduction half reaction. Still going to be 0, negative of 0 is 0, right? Now, if we take that hydronium ion, that's a solution. Standard conditions would be an activity equals 1. It's okay. Every textbook I've ever seen says, molarity of 1's good enough. Same with this, bar, 1 bar, 1 atmosphere is close enough. They're used interchangeably in pretty much every textbook I've ever seen. Plus the 2 electrons, right? 1 electron, right? So you're losing 1 electron per hydrogen atom. So we from the hydrogen. So we end up with 2 electrons there. So, that's a little more realistic, but pretty much every single electrochemical table I have seen simplifies it. And instead of using the hydronium and having the water here, they just use the H+. They just use the H+ for that, all right? So we can rewrite this, and I know you're going to appreciate this, as hydrogen gas at 1 bar pressure, giving us 2 hydrogen ions at an activity of 1 or molarity of 1 plus 2 electrons. So that's why I boxed that one. Even I'm not a fan of the H+. I'm a hydronium ion guy myself. But since every table we're going to see electrochemical tables here. All right, so we're going to be using Oh, I got a kitty coming. Pause. Oh, no, never mind. Bye, Beej. All right, so we're going to be using electrochemical tables. I'll be talking about in a little bit. So whenever you look for the value of 0 here, you'll see the hydrogen, and you'll see it as an H+. All right? So on this table, it's backwards from what I have written, but you'll always see it as an H+. So sometimes you'll see me write equations with hydronium ions for the half cell reaction, sometimes with H+. I'm okay with either one, but you'll find this one's easier. So we're going to take that particular half reaction and call that 0, defined reference, all right? And this would be, again, at standard conditions. And if we wanted to actually draw this, say we were drawing an electrochemical cell, a galvanic cell or electrolytic cell, whether it's spontaneous or not spontaneous, we're going to draw it like this. It's a little more complicated because the ones we did before, the actual reacting species was a metal, copper, zinc, silver. So we can make the electrode of the actual metal and fold it over and connect an alligator clip to it, or solder a wire to it or whatever. You can't do that here. There's no solids. No, what do we do? That's a gas. I can't connect an alligator clip to a gas. Having issues here. I can't do it to a solution. Sloosh, sloosh. Right? You can see the technical difficulties of that. So we need something for the electrons to flow. So we need a metal. It has to be a metal, and it can't be reactive to the solution. So it has to be a non-reactive metal. So platinum's by far the most common. It doesn't have to be platinum, but pretty much every textbook I've ever seen uses platinum. So what we're going to do, we're going to take a small sheet of platinum here, connect a platinum wire to it, and that's where the alligator clip connects in lab. That connects to the voltmeter, all that kind of stuff, right? So this is a non-reactive inert metal that we're going to use as the electrode, but it's not part of the reaction. Let's have a little beaker with a solution, right? An acidic solution with H3O plus or H plus of an activity of 1 or a molarity of 1's okay. And it doesn't matter what the anion is in that scenario, okay? Probably nitric acid or something. The hydrogen gas, that's a little trickier. How do we get the gas in there? So usually what we do is we have this glass tube with an inlet port here, right? And inside that glass tube is where the platinum wire is. and the little sheet of platinum that's submerged in this acidic solution. And we can connect this to a tank of hydrogen, some purified hydrogen, set that to a pressure of 1 bar, approximately 1 atmosphere, standard conditions, and we can bleed in the hydrogen gas, and then it comes through, and then hydrogen bubbles. You'll see hydrogen bubbles in the acidic solution there, right? So depending on which way the reaction is going, as written here, the hydrogen gas is becoming H+, so it's going this direction. If I flip this, this is as an oxidation or anode. If I flipped it and made it a reduction or cathode, I would just change the arrow. It would be going from H+ to hydrogen gas. Whoop-de-doo, same value of 0. We're going to find that the tables we use always have everything as a reduction half reaction. So you'll see it flipped the other way. But we're going to utilize this reference point as an anode. And what we can do now, this is the cool part of it. I can now, with a 0 reference point, just like with the third law of thermodynamics with the 0 point for entropy, I can now connect any other half cell to this one, right? This is a 0. So if I call this the anode every time, and I connect on the left-hand side, in the little beaker, this would be on the left-hand side, so I can put a beaker on the other side with any other half cell. I can do zinc, metal, lead, whatever it is, doesn't matter what it is. Connect them together, stick a voltmeter in there, and measure the whole cell potential. So what we need is an equation that relates that entire cell potential to the individual half cell potentials, and if this one is 0, then the other one must be equal to the overall measured on the voltmeter. Oh, nice. So using this as a reference point, we can get the half cell reduction potential for any other half reaction combined with this. And that is what's listed on your electrochemical tables. Look at all those beautiful things, so painful. All right, let's talk about how that works. We'll do examples on another video. I like to do mine pretty involved, showing the half reactions, showing the overall, where the electrons are flowing, drawing cells. I like the whole buffet, you know what I mean? But a lot of times you can do these really quickly. So let's draw up some line notation and show you how we can get individual reduction half cell potentials at standard conditions. Remember, we're stuck at standard conditions. All right, let's clarify how we're going to be using this defined 0 volt reference state. So we could write it as an oxidation half reaction with the hydrogen with an oxidation number of 0 going to an oxidation number of +1. And again, we could use hydronium ions or hydrogen ions. Either one's okay. And that has a value at standard conditions of 0 volts. We are going to use that to determine the reduction half cell standard potentials for all other species. So you'll most commonly see it written like that. All right? But sometimes you'll see it written as a reduction half reaction where the hydrogen ions or hydronium ions in a +1 oxidation number pick up some electrons and are reduced to the hydrogen gas with a 0 oxidation number, okay? And picks up an electron, goes from +1 to 0. That would be written as a cathode, okay? So as an oxidation half reaction, it'd be written as an anode, given a value 0. Written as a reduction half reaction, it's a cathode, given a value of 0. You'll see this listed on the electrochemical tables like I showed you, right? You got the electrochemical tables, you look for the value of 0, and there's your H+ going to H2 gas. Now, because we need the platinum, sometimes you'll see people put platinum over the arrow. You need the inert metal to conduct the electrons. Not critical, right? But sometimes you'll see a platinum written up above there. Yeah, whoop-de-doo. Again, I will put a star next to this. That's how we're going to be utilizing it, but that's how you see it on a table. But you don't even need a table because it's 0. It's defined as 0. And we're going to find if you reverse an equation, you change the sign on it. Right? So changing, like I said, -0 is 0. We like values of 0. If we write this as a line notation, I showed you how to write it as a cell diagram, right? Writing a galvanic cell with the beakers and the tubes and the hydrogen gas port. Big pain in the butt. Depending how artistic you are. I'm pretty crappy at Pictionary, but as long as you have a psychic network connection with your another player, it doesn't matter how crappy your picture is, they can figure out what it is. Blah, that's Michigan. Blah, that's the Statue of Liberty. Yay! if you're going to draw it, try to do it as best you can so I can see all the component parts. It doesn't have to be beautiful. You don't have to be an artist, right? But I got to be able to see the component parts. So as a line notation written as an anode, you can condense this, right? If you look at that beaker that I drew, you've got the platinum electrode, the anode. You put the vertical line to represent a different phase. We've got the hydrogen gas, right? We're going from hydrogen gas at 1 bar pressure. If you know the pressure or you know the concentration, write it in there. If you don't, just write gas or AQ. And then we draw, since the solution is a different phase from the gas, we draw another vertical line, and then we put what it forms, the hydrogen ions, with an activity of 1, molarity of 1's okay. And again, you could put 1 atmosphere here. And then the salt bridge, right? Remember, we do those 2 vertical lines. Some people do dash lines for that. That represents the half of the line notation diagram representing the anode. And then you would insert any cathode on the other side. If you want to really do shortcuts, since we do this so often, instead of writing all of this garbage, because it's the same every single time, just write standard hydrogen electrode, or SHE, S-H-E, like on the last video. Standard hydrogen electrode. It's SHE, all right, with the vertical dash line. And then you just connect the cathode on the other side. Always do the anode on the left, cathode on the right. So let me briefly talk about how we're going to use these. And if we reverse signs, I'll officially write that up. If we reverse reaction, we change the sign on it. And then we'll look at overall cell potentials on the next video. All right, here's how we're going to utilize this reference state of 0. All right, I've talked about it, but let's write it down. Make it official. We'll officialize it. We can connect any other species, like I said, as a reduction half reaction, written as a cathode on the right-hand side, to the standard hydrogen electrode, or SHE, as an oxidation half reaction as the anode on the left-hand side. So anode here, cathode there. We can do line notation. We could draw the beakers and all the connective wires and the salt bridge and all that fun stuff. By doing so, we can now measure the overall cell potential. Stick a voltmeter in there, stick the standard hydrogen electrode here, stick the other species there, put the salt bridge in, boop! We get an overall cell potential difference between them. Yay, we can measure that. I can't measure the individual electrodes, but I can measure the difference, right, between them. So when we take it, and again, we're limited to standard conditions. We'll do non-standard conditions later. Same thing happened with Gibbs energy, right? We did standard conditions, then we had to convert that to non-standard conditions with an adjustment factor. We do the same thing here in electrochemistry. So when we get the overall standard electrode potential, the potential difference between the 2 electrodes, we can measure that. We can then calculate and determine the reduction half cell potential of the unknown one on the right-hand side relative to the standard hydrogen electrode on the left-hand side as the anode, because that's 0, right? So we can get the reduction or standard reduction half cell electrode potential for any species written as the cathode relative to the standard hydrogen electron. This is fantastic, right? Those are tabulated. Yay. I'm going to go let a yelling kitty out. I'll be right back. All right, happy cat. So again, here's the tables. So you'll have these in your appendix in your textbook. And so these are all written as reduction half reactions as cathodes connected to the standard hydrogen electrode. And these are all the values. I'll show you how we do that in the next board. Okay, so some are positive, some are negative. Goes on to another page. And these are all in acidic solution, and then you have some that are in basic solution as well, which works out. So let me show you how we actually connect it and how we get those values. All right, I could have picked any half reaction here for a reduction half reaction, but let's take our standard hydrogen electrode as our oxidation half reaction at the anode. That has a defined value of 0. Whether it's written as reduction or oxidation, anode or cathode, doesn't matter, still 0. We could take any other reduction half reaction. We could reduce zinc, iron, any metal, you name it. Let's just do copper because you saw the copper ones. I could have done zinc. We did copper and zinc. I think they were the 2 metals we saw. I want to do the silver, but trying to find a nice strip of silver, yeah, right, or gold. Yay, let's do the gold. Go sell it on eBay. So if I take the copper 2, pick up 2 electrons to get copper solid, I'm reducing it. So that would be as the cathode. So we'll do the cell line notation, we'll do the beakers and all that kind of stuff and show you how these all look. But if we add these two together, I always like you to do the reduction and oxidation half reactions and identify those electrode potentials. We don't know what the cathode electrode potential is, and this is the standard conditions. That's why we've got the little knot symbol there. That's an unknown, okay? So the key is, but I can measure the difference between them. Hey, so let's hook this up in the lab. Let's do it. If I add these two equations together, just like we've done before, the electrons cancel out. If they didn't, I'd have to multiply the equation to balance out the electrons. Add them together and you get the hydrogen gas, and I'll stick in the 1 atmosphere, 1 bar there. The copper ions, 1 molar, activity of 1, giving us the hydrogen ions or hydronium ions, activity of 1 or molarity of 1, and the copper salt. That's our overall reaction. We can measure the overall cell potential. Right? We can hook it up in lab, use a voltmeter, boom, we got it. So all we need is an equation that relates all this. Now there's 2 different ones that I've seen. I have a preference, but what we can do is E naught cell, the overall cell potential at standard conditions, this is also true at non-standard conditions, is equal to the cathode individual half cell or electrode potential plus the individual electrode potential at the anode. Now I've seen it that way. I've also seen it the other way. If you take the cathode minus the anode, I'm not a fan of that because then you got to remember which one comes first, okay? But I've seen textbook used both ways. I grew up learning it this way, so I'm going to teach it that way, even though our particular book that we use does it this way. I don't care which way you do it, but you just have to remember the trick for it. If you add them together, we're going to have to figure out the individual ones, and then I'll show you the trick to that. If you subtract it, you can use the values straight from the tables here, and you don't have to reverse anything around. So I guess mathematically it's a little bit easier, but it doesn't follow logistically from my point of view. I like to get the cathode, because remember, all of the values listed on that table are as cathode reduction reactions. Well, that's not a cathode, that's an anode, right? So to get the anode, you have to flip the cathode around, all right, and change the sign on it. So what I do is I take these, but I have to reverse the reduction reaction from the table and change the sign. So if I do it straight up as an oxidation half reaction, I find it on this table, but that's written as a reduction. So what I do is I just reverse the equation, and then it matches the equation I have written, and all I do is just change the sign. So on this table, it's written, right, what I showed you, as the H plus 2E minus, giving you hydrogen gas, which is the reverse of this. So if I flip this, if I reverse this equation, I put a negative sign in front of the 0 volts. We'll talk about that on the next screen. But the cathode one I don't have to change. That's why some people like this, they just take the value right off the table, and that negative sign accounts for the fact that it was reversed. Okay, whichever way you prefer, I don't care, you're going to get the same answer. This is just a little more logistical from my point of view. All right? So would you agree, if I can measure this overall cell potential, and I know this by definition, can't I solve for that? Oh, let me show you how to do that on the next board. Easy peasy. Ready for some cool pictures? All right, here's the overall electrochemical cell. So we've got the standard hydrogen electrode. We've got the hydrogen gas, coming in through the port. We've got the glass tube. We've got the platinum plate and wire attached to the voltmeter there. We got the bubbles of hydrogen gas coming through with the platinum. That's the anode. And then we got the hydrogen ions, right, at standard conditions. That connects to a voltmeter, so these electrons are generated at the anode. They flow through to the cathode, which is the solid copper. In this case, could be any other species. And that copper metal, like a foil or whatever, is connected into a copper 2 solution, maybe copper 2 nitrate or sulfate or something, of 1 molar. And then we connect it by a salt bridge. So as we produce the hydrogen ions, the nitrate ions flow over to electrically balance it. As the copper ions are lost, 2 potassium ions come over to electrostatically balance that. And when we pop that salt bridge in, we get a value of positive 0.340 volts. That's the cell potential at standard conditions. And if we do the line diagram for that, you can see the standard hydrogen electrode here, salt bridge, copper ions going to the copper solid. So that is the overall reaction. So let's calculate. We know this. That's 0 volts. We know the overall. We don't know that. So let's calculate the reduction half cell potential of just the cathode using some rules that I've talked about. All right, let's polish this off, gang. This is how we do it. I'm not going to make you, I'm just showing you where all these numbers come from on these electrochemical tables. You never need to do this again, although we will follow this pattern. All right, here's some rules. When a half reaction is reversed, so if I take anything on here and reverse it, I change the sign on that. All right, that's rule number 1. If I multiply any of these equations by a factor of 2 or 3 or 1/2, which we have to do. Remember, if the electrons don't balance out in the half reactions, you have to multiply them so that the electrons do cancel out. That's a key factor when you're adding half reactions together. What are the rules? Well, what's interesting, these electrode potentials are intensive properties. They're independent of the amount. It doesn't matter, right? You've got a waterfall. Doesn't matter how much water's going over. The height difference stays the same. This is not true for thermodynamic properties and equilibrium problems and kinetics problems. So if I multiply any of these equations by 2, 3, 4, or 5, that value doesn't change. Hallelujah. Finally, we got something where it doesn't change. We don't have to multiply it by 2 or raise it to the power 2 or something stupid. Remains unchanged. So using this equation where the overall standard electrode cell potential, and this is also true at non-standard conditions we'll do later, that will be the cathode electrode half cell potential plus the anode half cell potential. Or if you use the other equation, right, you'll see the minus sign there, but it's a little different. So I'm solving for the cathode potential of this unknown copper half cell as a cathode. So that copper reduction as a cathode will be the overall cell potential, which we measured on the voltmeter, which I showed you in the picture, minus the value of the anode, which is the standard hydrogen electrode value 0. So this is what we measured on the voltmeter, positive 0.340 volts. Subtract the value for the anode, which is defined as 0. So the half cell potential for the cathode, the reduction, is just what's measured. That's why we love the reference state of 0. So we get the positive 0.340 volts. So we can do that for every species connected to the standard hydrogen electrode as the anode. Do this, and these are the values you get, my friends. So these are half cell reduction standard potentials for everything written as a cathode. Right? And if you look up the copper, at 0.34, where is it? Where is it? I can't see it. There's the 0.340. You see the copper being reduced? That's why it's 0.340. So we can use this as values for those as cathodes, but if we use it as an anode, we reverse the equation, we reverse the sign, and we can use that equation. Yay! Let's do it in another video.